Hello, this is MAT221 Calculus 1. This is section 3.7. We're talking about derivatives of logarithmic functions and logarithmic differentiation. So here when we start talking about logs, remember we go back to our definitions of logs and properties of logs that we know from earlier courses, from pre-calc or from Algebra 2 Trig or Algebra 2. Remember, if we say y equals the natural log of x, that is equivalent to e to the y equals x, because remember, natural log has a base of e that is not written, and e raised to this exponent of y will give us this result of x. So that was the definition of how we defined a log, right? We would take that base raised to this exponent will give me this answer. Or in other words, this y is the exponent of the base that will give the answer of x. Now that we know that, we remember that from previous lessons, we're going to actually derive the derivative of the natural log of x by using our properties of logs and the chain rule and implicit differentiation. So if I took the derivative of each piece of this function, the first thing is I would say, well, let's take the derivative of e to the y. And remember, by implicit differentiation, this y and this x do not match each other. So we would technically be using the chain rule here. And the derivative of e to something is itself multiplied by the derivative of the inside function. And the derivative of x, of course, we know that because these will match, will equal 1. So when we take the derivative implicitly, we get e to the y times dy dx equals 1. Now solving for dy dx, solving for the derivative, we get the derivative of y with respect to x is equal to 1 over e to the y. But we know right here from our substitution here, we know that e to the y is actually equivalent to x. So we know that the derivative of this function, which is the natural log of x, is now equal to 1 over x. This is the rule for the derivative of the natural log of x. Now, the one thing that we know here, so this is our next rule in our many rules of shortcut rules. Now, one thing we will notice, though, is most of the time when we're given the natural log function, we're not just given the natural log of x. We usually have a function within the natural log function that we have to take the derivative of. And there we would have to then use the chain rule. So often when we do the natural log of x, we take the derivative of the natural log of x, we have to incorporate the chain rule. So let's look at this formula if we were to incorporate the chain rule. If we were to incorporate the chain rule, we would say, what is the derivative of the natural log of some function where there's an inside function? Remember, using the chain rule, we would do the derivative of the outside function, which would be 1 over something, leaving the inside function undone or left alone. So it would be 1 over the function, and then times the derivative of the inside function, which is f prime of x. So we're using, this is the derivative of natural log, but it is incorporating also the chain rule, because often when we have a natural log function, it incorporates another function within the natural log. Now, we could just simply use the chain rule as we usually did, but again, incorporating this this new rule for natural log. So the derivative of the natural log of some function is equal to 1 over the function times the derivative of the inside function. Now, if we go back, it makes sense here too, because remember, the derivative of natural log is 1 over the function, which is just happened to be x, times the derivative of x with respect to x, which is just 1. So it would be equal to 1 over x. So let's try a couple of examples. What about if I had the derivative of the natural log of sine of x? Now, using this rule, notice again, we're incorporating the chain rule because we have a sine function within the natural log function. So using this rule, it would be 1 over the function, sine of x, times the derivative of the inside function, which is cosine. And we know that cosine over sine is equal to cotangent. So we could simplify this one. Let's try another example. What about if I asked you for the cosine of the natural log of x cubed? So now we actually have a triple chain rule here as we move along. So we have this rule here, which is the chain rule incorporating the natural log, but then it's within the cosine function. So let's take it apart and see what we have. We have the derivative of the outside function, which is cosine. The derivative of cosine is negative sine, leaving the inside function untouched. So now we've done the derivative of cosine. Then we use the rule above to find the derivative of the natural log of x cubed, which also incorporates another chain rule. The derivative of the outside natural log would be 1 over the function, leaving the inside function untouched, times the derivative of the inside function, which is 3x squared. This is the derivative of natural log, also incorporating the chain rule. So I could reduce this a little bit and then simplify to get negative 3 sine of natural log of x cubed all over x. Now to find the derivative of the common log function, we could use the change of base formula that we had back in pre-calculus. The change of base formula says this, that the log to any base, in this case base 10, of x is equal to the log of x, the natural log of x over the natural log of the base. But remember, the natural log of 10 is just a number. So this actually can be written as a coefficient of 1 over this, which is actually a number. So I'm pulling out that coefficient of 1 over the natural log of 10, which is just a number. So I'm using the constant multiple rule by just pulling out that constant, pulling out that number, and then taking the derivative of the function. But this one we already know. The derivative of the natural log of x is just 1 over x. Therefore, we see that the derivative of log to the base 10 is equal to 1 over x, just as we saw with natural log. But then we're just going to multiply by 1 over the natural log of the base, which will be true for any base. For the formula for a derivative of a log of any base other than e is equal to 1 over the function x multiplied by the natural log of the base. Again, so here's our next rule here. Here's our next rule. We have the derivative of a log to any base is equal to 1 over x times the natural log of whatever that base is. Now again, often when we're given these functions in calculus, we don't just get the log to the base 2 of x. We usually get log to the base 2, and then x is often a function. So often we would incorporate the chain rule. So up here in this box, you can see that I incorporated the chain rule here. The derivative of a log to any base, when I have a function inside it, when I have an inside function, is equal to 1 over the function times the natural log of the base multiplied by the derivative of the inside function. So these two are two rules that we use, but we're incorporating the chain rule within each of the log's formulas. The log formulas by themselves are just these. This is just the log formula if I just have x. But if I don't, and I have something more, then I can incorporate this rule. All right, so let's do it on this particular function. What about if I took the derivative of log to the base 2 of the square root of x? Now notice I have an inside function. F of x here is the square root of x. It's just not x by itself. So this is equivalent to taking the derivative of log to the base 2 of x to the 1/2 power, because we know radical x is equal to x to the 1/2 power. Now incorporating the chain rule with our new rule here, it would be 1 over the function, so 1 over x to the 1/2, multiplied by the natural log of the base, which is the natural log of 2, times the derivative of this inside function, which is 1/2 x to the negative 1/2. And again, simplifying a little bit, putting my value variables together here, doing a little bit of algebra. Remember, x to the 1/2 is actually going down to the denominator, becoming x to the positive 1/2, and x to the positive 1/2 times x to the positive 1/2 would be x to the first, and then the 2 would be brought out to the front. So this would be my simplified version of this example. The next thing I wanted to talk about is a process called logarithmic differentiation. The calculation of derivatives of complicated functions involving products, quotients, or powers can often be simplified by taking logarithms. In other words, using our properties of logs that we learned in earlier courses, or if we look back in Unit 1 from pre-calculus, our pre-calculus review, this method is called logarithmic differentiation. Now, just a little bit of a review before we get into this. In general, there are 4 particular cases when we talk about exponents and bases. So if you look, if I had a number raised to a number, where in other words, a and b are both constants or both given as numbers, if I have a number raised to a number, that's just a number. And the derivative we know of just a number is equal to 0. That's our very first rule that we learned in the very beginning. Or if we look at step 2 here, we could have a function raised to a number. Now remember, that would be like x squared or x plus 5 to the 5th, where we have a function raised to a number. We have a rule for that for our derivatives. And what it is it's the product, it's the power rule. And the power rule says we would bring the number down to the front, leaving the inside function untouched, and then subtract 1 from the exponent, and then take the derivative of that inside function. So it is both the power rule and the chain rule here. All right, so we have a rule for a number raised to a number. We have a rule for a function raised to a number. Now let's look at a number raised to a function. Well, that would be the exponential rule, because if I have a number like 2 to the x, or 5 to the x, or 5 to the x squared, we would be using the exponential rule. So we have a rule for that. That would be a to the g of x, so it would be using the chain rule. It would be itself times the natural log of its base, and then multiplied by the derivative of that inside function g of x incorporating the chain rule. Now, the 4th scenario down here, however, we do not have a rule for this. To find the derivative of a function raised to a function, we have to use logarithmic differentiation. We have no rule that we can use for this case. So again, let's go through the 4 cases. If I have a number raised to a number, that's a number, derivative is 0. If I have a function raised to a number, using the chain rule and the power rule, I have a rule for that. If I have a number raised to a function, I have a rule for that. That's the exponential rule and the chain rule. But if I have a function raised to a function, I don't have a rule for that, and I'd have to use logarithmic differentiation. So here's our procedure for logarithmic differentiation. How do I take the derivative when I have this form? So here's the steps. What we do is we take the natural log of both sides of the equation and then use our rules or laws for logs that we learned in pre-calculus and before to simplify the expression. Then step 2 will be to differentiate implicitly with respect to x along each term of the expression. And then lastly, we solve for dy dx. So let's look at this first example. Notice we have to use logarithmic differentiation because we have a function raised to a function. We have a variable raised to a variable. We have a function raised to a function here. So we must use logarithmic differentiation.